Okay, kids, so here we are. Part 4 of the nuclear chapter. And this is nuclear reactions. But before we get to the heart of the nuclear chapter, which is nuclear reactions, we have to go back a little ways and review. There are two things that we have to review: natural transmutation and artificial transmutation. Don't forget, natural transmutation means the radioactive isotope or the radioisotope just spits out stuff by itself. And remember, it can spit out a positive alpha particle, which means the new radioisotope will go down 4 in mass and 2 in atomic number, or it spits out a beta particle, which is a high-speed electron. That means the mass stays the same, but the number goes up by 1. Or it spits out a positron, which means the mass stays the same and the atomic number goes down 1. Those 3 are called natural transmutation. You don't need anything to make them do it. They do it spontaneously. But the ones we're concerned with today, it's called artificial transmutation. And we did that in the last chapter. And what that means is you have a stable isotope, like aluminum, and you hit it with something. So what do you hit it with? Well, you can hit it with an alpha particle, a beta particle, a positron, a proton, or a neutron. So, where do we get those things to hit the stable isotope with? That is where we're going to start. And these things that produce all these little subatomic particles that smash into the stable isotope's nucleus, they are created from particle accelerators. And that's where we're going to start today. So, particle accelerators accelerate charged particles. So, what are charged particles? Well, we'll open up a parenthesis. Charged particle, a positive proton. A beta particle, or a negative electron. A positive electron, that's called a positron. Or the biggest one of all, like I told you, like a bulldozer, the alpha particle. Those are some of the charged particles that will hit the stable isotopes and make them unstable, because remember, these crash into the nucleus and change the nucleus. Okay? Now, the one very cool thing about these particle accelerators is we have one 30 miles away from Elmira at Cornell University. At Cornell University, they have something which they made in 1938, and that is called a cyclotron. It's a circle, and it has electromagnets all the way around it. And the particle has to be charged, and they turn on and off the positive and negatives, and it makes the particle go faster and faster and faster and faster and faster, and finally it smashes into whatever they wanted to smash into, like a stable isotope of some element. Okay? Now, that was an old one, and that was called a cyclotron that Cornell has, but now they have something brand new. And it is really a huge underground tube. And here's a picture of it. So here's a picture of Cornell University, and that's Alumni Field. And this tube is buried 40 feet below. My physics class back in 1990s was actually able to climb down into it and look at it. It's about a half a mile around, pretty cool, and it's called the Cornell Electron Storage Ring. And it is an electron-positron collider. And that's what makes some of the subatomic particles go round and round and round until they hit a stable isotope and smash its nucleus and make an unstable radioisotope. Pretty cool. Now, they have circular ones called cyclotrons, and they also have straight ones called linear accelerators. And the biggest linear accelerator in the world is in California. This is the Stanford Linear Accelerator, and you won't believe how long it is. Yep, it's 2 miles long, and it accelerates electrons to an incredible speed to smash the nucleus of different stable isotopes. So, particle accelerators accelerate charged particles. But we didn't talk about one subatomic particle that particle accelerators can't accelerate because it has no charge. It can't accelerate neutrons. Why can't it accelerate neutrons? Because a neutron has no charge. So what they have to do is what we're going to be talking about today. They have to find radioisotopes that give off neutrons. And neutrons are kind of perfect to smash into the nucleus of another atom because neutrons have no charge. Remember, the nucleus is positive. So it's really hard to hit a nucleus of a stable isotope with a proton because proton's positive. Chances are they repel. An electron, they're teeny. They're really teeny, so they don't really do very much damage. And positrons, they're positive, so the nucleus may repel it. Alpha particles are positive, so chances are the nucleus will repel that. So neutrons are what we're looking for. Neutrons can smash into the nucleus and really change it up. And that's what you have to know for the next topic today. Einstein, Albert Einstein. What can I say about him? He's supposed to be the smartest man that ever lived. When he died, they took his brain out to study it, and they still have it. Yeah, they still have it. And he's won the Nobel Prizes for everything. The one thing I hate to tell you is when he took entrance exams to get into one of the schools, he failed the chemistry exam. But in math and in physics, he aced them. And remember, Einstein, we'll talk about him a lot later when we do the making of the atomic bomb lecture. But Einstein did this theory, E equals mc squared. So what that means, right now in chemistry, E doesn't stand for energy. In chemistry, Q is energy, but back then E is energy, M stands for mass, and c squared is the speed of light squared. So what he figured out is if I took about a 2-pound mass, now you've never heard this word before, but we're going to talk about it, a 2-pound mass of a fissionable radioisotope, 2 pounds, and then multiplied it by the speed of light squared, a 2-pound mass of a fissionable isotope, if it were split, if the nucleus could be split, it would produce an explosion, 20,000 tons of TNT. 2 pounds! And he knew this. And this formula actually led to the making of our atomic bombs in World War II. But Einstein lived in Germany. And in the early 30s, the Nazis were coming to power. And for some reason, they hated the Jews, which was really good for the US because almost all the top physicists that were scientists in Europe were Jewish. So guess where they ended up? Yeah, they ended up in the United States, which was really good for us. Einstein was the head of physics at the University of Berlin, one of the most famous universities of all in all the world. But in 1931, he goes, hey, things are getting a little bit too rough here. So he came to the U.S., settled around Princeton, New Jersey, and yeah, that's how we got most of our top scientists that were in this thing called the Manhattan Project that we're going to talk a lot about later on. The Manhattan Project made the atomic bomb. Okay, so now we have to talk about this. E equals mc squared. There's E equals mc squared. I already told you what that stands for. And here is what the deal is. That formula, the conversion of a small amount of, and there's that word again you don't know, we will in a minute, a small amount of fissionable mass into a tremendous amount of energy. Remember the 2 pounds and the 20,000 tons of TNT? Yeah, that's a lot. All right. Now, there are 2 types of nuclear reactions. We are only going over one type today. And the type today is called fission. And look, it's right there in the word fissionable. Okay? So, if you have your black notebooks, this should be written in there. And then we are going to put this down. There are 2 types of nuclear reactions. A, the one we're going to talk about today, is fission. The next video will be on the second type of nuclear reaction, and that is fusion. So here we go with fission. And if you have your black notebooks, you should write this down. Fission, the splitting of a heavy fissionable radioisotope into lighter radioisotopes. In red, I have some neutrons. That's going to play a huge part, and a tremendous amount of energy. Now, what the heck does fissionable mean? Remember I told you that there's at least 3 isotopes for every single element. Okay. Now, and at least one is radioactive. Well, a fissionable radioisotope means one that when you hit this radioisotope with a neutron that has to be moving slowly, it will split the radioisotope into pieces, like it says here, give off a lot of energy, but most importantly, it'll spit out a few neutrons. And these neutrons will hit more of the fissionable radioisotope, and if one of the neutrons hits another nucleus, 3 more will come out. And those 3 hit 3 more, 9 more will come out. And it happens in a millisecond. So what we're talking about is we're talking about a radioisotope that when you hit it, it not only gives off a huge amount of energy, it gives off several neutrons to continue the chain reaction. And that's what fission is all about. So during the time they were making or trying to make the atomic bomb in the 1940s, they looked at every single isotope of almost every single element to see which one gave off neutrons when it was hit. And they mainly came up with just 2. Just 2. And we'll be talking about those 2 later on. Okay. So now I want you to put down letter B. And I said the nucleus of the fissionable radioisotope has to be hit by a neutron, but it has to be slow moving. I'll explain that in a minute. But remember, neutrons can't be accelerated by particle accelerators because they have no charge. So let me explain. First of all, when this fissionable radioisotope is hit by a slow-moving neutron and it splits up into a lot of energy, a lot of little particles, and 3 wickedly fast-moving neutrons, those fast-moving neutrons have to be slowed down. Because, like an analogy, you've ever been bowling and there's this real tough guy and he throws that bowling ball super fast down and the bowling ball hits the head pin, but it goes straight through and it leaves pins on both sides. It was going too fast. So then you get this other person comes up, he throws it moderately down the bowling alley and it hits the head pin and they all fall down. So the slower the neutron is, the more it will penetrate the nucleus and break it apart. Because the fast-moving neutrons will just zip right through the nucleus without breaking it apart. So it has to be a slow-moving neutron. And there are several substances that we have to talk about that slow down the neutron. And one of the substances that we will really be talking about is called heavy water. And another substance that will slow down the neutrons is graphite, like what is in your pencils. Okay? So for letter B, must be hit by a slow-moving neutron. Now, remember, once these neutrons come out and they're slowed down, they hit more and more and more nucleus. And so this is called a chain reaction. Now, there's two things we can do with that chain reaction. The first thing we can do with the chain reaction is, if we just let the neutrons hit all the other fissionable nucleus of the radioisotopes and don't control it, it's called an uncontrolled chain reaction. An uncontrolled chain reaction, well, that's called an atomic bomb. So an uncontrolled chain reaction is called an atomic bomb. A controlled chain reaction. Well, what's that mean, controlled chain reaction? Well, obviously, we have to control the number of neutrons that are hitting the other fissionable radioisotopes nuclei. So if we control the number of neutrons, we can control the reaction. And what is that? That's not an atomic bomb. That is this. A nuclear reactor. So if we control the number of neutrons hitting the other nuclei, it's a nuclear reactor. If we don't control it, it's an atomic bomb. All right? Now, what we're going to do right now is I'm going to give you the formula for fission. And after we do the formula for fission, then I'm going to explain how a nuclear reactor works. Before I give you the fission equation, which is really long, we have to talk about the fissionable isotope that is usually used. And it comes from the element uranium. Now normally, remember the uranium disintegration series, it starts with uranium-238. But uranium-238 is not fissionable, which means when you split that nucleus, it does not spit out a bunch of neutrons. But uranium-235 is fissionable. So that's the one we want to use. The problem is this. Of all the uranium in the world, only 0.7% is uranium-235. All the rest is uranium-238. So they have to use tons and tons of uranium and separate it, uranium-238 from 235, just to get enough to use in nuclear reactors. And we are really going to be talking about that during the making of the atomic bomb, because they needed tons and tons and tons of uranium to try to separate the 238 isotope from the 235. But we're going to be using uranium-235 that is a fissionable isotope. All right? So now, here's part of the equation. Okay, so we have uranium-235. And remember, we have to hit it with a slow-moving neutron. So uranium-235 plus slow-moving neutron. Because like I said before, when they come out of the nucleus of uranium-235, they are really, really fast. And they would go right through the nucleus without splitting it up. So remember the two things I told you that's going to play a part in our further stories coming up. Heavy water and graphite are the two main substances that slow down neutrons. So we've got a slow-moving neutron crashing into the nucleus of a fissionable uranium-235 isotope. Now, remember what I told you, that big old fat nucleus splits up into smaller ones. And here are the smaller ones. One is krypton and one is barium. Okay, R plus Ba. And krypton is atomic mass 92 and atomic number 36. Barium is 141 and 56. All right, so these are called radioactive waste products. We're really not interested in those for anything, but it's waste and it's radioactive, so we have to be very careful with it. Now, the things we're interested in, these things we're interested in. 3, for every nucleus, for every uranium-235 nucleus that's split up, we get 3 neutrons. Remember, they're wickedly fast. So we got to slow them down. And the other thing we get is this. Q. And remember, Q means energy. All right? So this is what we have. Uranium-235 hit by a slow-moving neutron. We get some bad stuff, radioactive waste. 3 fast-moving neutrons and energy. Now, the cool thing about this is, this uranium-235, I'll put it down here, 235, 92. If you look, 235, 92 plus 1 neutron, that would be 236 for mass over here. If you look over here, 3 neutrons, barium, and krypton, that equals 236 for mass. And 92 here, 36 and 56, that's 92. So all the mass and the atomic numbers on the left equals all the mass and the atomic numbers on the right. So this is the formula for nuclear fission. So one more time, because you're going to be tested on this quite a lot. A fissionable uranium-235 nucleus is hit by a slow-moving neutron. This fat, huge uranium-235 nucleus explodes into radioactive krypton, radioactive barium. There may be some other radioactive waste products, but we're mainly interested in those two. Most importantly, 3 fast-moving neutrons to continue the chain reaction, and an awful lot of energy. All right? Now, that's how it works. And the next thing I'm going to show you is how a nuclear reactor works. Okay? Remember, we have nuclear reactors here in the United States, and everywhere else. France has the most nuclear reactors, and that's where they get the majority of their energy from. Now, a nuclear reactor does basically the same thing that any power plant does. So here's how a power plant works. In fact, we have one. It's called Hickling Station, and it's about a mile from this school. And it's located on the Chemung River. So here's how it works. A power plant has to be located near water. And what happens is they take the water in, and either by coal or by oil, they turn the water into steam. And then the steam goes through turbines, and the turbines produce electricity. That's how a power plant works. Now there's a couple problems, because that river water or lake water or whatever it is, that turns into steam. That's super hot. So remember, it has to go back into the river, but they have to cool that water down before it goes back into the river, because remember about the solubility of a gas in a liquid? All the oxygen would be out of that hot water, and that would kill all the fish. So they have to cool down that hot water to very close to what the river water temperature is before they put it back in. All right, we're going to be talking about that. So that's how a power plant works. So how does a nuclear reactor work? It draws in water, and this reaction produces the heat that's going to turn the water to steam, and then the steam will turn the turbines, and the turbines will produce electricity. But it's a little bit more technical than that. So I'm going to tell you step by step of how a nuclear power plant operates. So here's your homework. On the first page, it's 1, 3, 4, 5, 6, and 7. On the second page, it's 9 through 15 and 10. On the fourth page, it's 12, 13, 15, and 18. And on the last page, it's simply 20 and 21. Now, what I want you to do is either you take a picture of the 4 pages with the answers on them and send them to me, or write down all the numbers with the answers right next to them and just send 1 page to me. Doesn't make any difference. This will be due for this Wednesday. Thank you.